timing queuing theory and information theory is somewhat more recent. People are able to do only recently. Earlier they were not able to combine the two. So, but finally, once you know how to do it, it doesn't turn out to be difficult, but took people 20, 30, 40 years in trying to actually combine the two disciplines. So this is a very neat result in that sense, which is what happens. This is a realistic model which is going to have energy buffer as well as data buffer. Then this is the result that you get. MAC policies, when there are multiple channels, each user has its own data queue, its own energy buffer. So QK1 is the queue length of user 1 at time k, EK1 is its energy, and there are n users, and they all have to use one channel, wireless channel. So this is MAC policy, this is for uplink. For this also we got the information theoretic results. This looks, if you are familiar with the capacity region for a usual multiple access channel, for this model also with buffers and so on and hard energy constraints, you get exactly the same thing, just like for the point-to-point case. And EY1, and this is for two user case, R1 and R2, and this should be R1 and this should be R2. So this is exactly the formula that you get for usual MAC, except that expected mean amount of energy that you are using at user 1, mean energy you are using at user 2, and they are sitting here instead of P1 and P2. That is the average power constraint that you see. So what it says is, as for point-to-point case, that the hard energy constraint is not having an effect. Again, here what I am assuming here is that all the energy is being consumed in transmission only right now. So, but when you also consider the energy consumed in other cases, then of course the things will change. There are some results available. We have not obtained those results yet. We are in the process of doing that, but we also have results where the energy buffer is finite in this case. Okay, and the things change somewhat. I don't have right now the figure which compares these two. Now these are again the queuing theoretic part. So that was the information theoretic. A couple of results that one can easily get is this is opportunistic scheduling for feeding channels. You assume channels to be now in this case the different well, you can forget this sentence here. Orthogonal channel. You have one channel available, just like before, and HKI is the channel gain of user I in slot K. Then a throughput optimal policy, again which maximizes the region, stability region, is in slot K choose a policy, choose the user. So this is the slot K. In slot K you are going to choose the user, which maximizes this. And what is this? QKI, that is the queue length of user I in slot K. GI is the function, that channel function that I said, which gives you the rate based on what power you are using. HKI is the gain of that user. This, there is a slight, you can replace this by this quantity. TK is the energy that you are going to use. So you are going to choose the queue which has maximum queue length and rate. This is basically rate if you use TK policy. Okay. Now TK policy, the TK is going to depend on the average energy that is being generated by user I. So it depends on that statistics. Just like in point-to-point case, you use a little bit less than average energy, but in this case you are also dividing by something, because this user I is not using the channel all the time, right? So that way, if you are using half the time, then we can multiply this quantity by 2 to get this thing. Of course, in this case you don't know, because the way policy is, you don't know a priori what is the fraction of time a user is going to use, and that we estimate online in the policy via LMS kind of algorithm. There is another, there is not CDMA, so CSMA based scheduling you can do. Now in Zigbee and Wi-Fi you use CSMA, right? There is a timer, back of timer, and this is what people use. Now you can tinker around with that. The back of timer, now you can make a function of again this index that I used in the last. Q length based on Q length and the power you are going to use. Power depends on the energy you generate and your channel gain at that time. Okay, so back of timer, you can make it as a function of this index, where f is some non-increasing function. So as this quantity increases, your back of time will become less, and those are the users which will time out first and try to access the channel. So these are some of the comparisons. This is for the first channel, where there is only one channel. There are symmetric situation, 3 queues. This is for CSMA, and mean delay is being plotted versus mean arrival rate. And these are the different policies. Okay, and this is so here, if you look at it, this is TDMA policy, and this is TDMA with water filling. So you do TDMA, each user being given certain fraction of slots a priori, and but whenever that is being used, it can use as channel gain and do the power control. So that will improve the performance a little bit. Then these policies, this is throughput optimal policy, the curve that I gave earlier, and this is then greedy with water filling and TDMA. So there are 5: throughput optimal, greedy, TDMA, greedy with water filling, and TDMA with water filling. So these are going like this. This was just TDMA. This is greedy. This is TDMA with water filling, and this is throughput optimal, and these are the other 2 curves. Okay, so you can gain significantly if you make a proper use of it. Here, channel gain information has been used, and the energy information has been used along with the data. And this is for the CSMA kind of thing, and you can see the difference. Here again, so this was just expansion of this part, but here is the usual exponential back off that is used in this thing. Wi-Fi, and there was a Zhang and Tong policy. They wrote a paper that is almost matching this only, so it doesn't really make a difference. The other are our policies, our policy and our policy with water filling. These are 2. So this is delay, and this is the mean arrival rate, and you can see there is a significant amount of difference. We have worked on multi-hop scenario also. There are multiple nodes. So this, for example, could represent either a sensor network with energy harvesting, solar panels on them and so on. There are multiple nodes. Some of them are sync nodes. Some other nodes may be transmitting data to some of these sync nodes. Okay. There are N. So we are considering here only stationary nodes, N stationary nodes, T sync nodes. It's a slotted system. Sensor nodes. These sensor nodes sense some random field. And Dn is these sync nodes for node n. So there is maybe multicasting here. A node can be in sleep or wake mode, so it can sleep, wake, and the nodes are generating energy via harvesting sources. So different nodes have different energy harvesting rates, and they may be generating data at different rates. So what we have to do is, we have considered joint power control. So it's link scheduling, because there are multiple links here. Routing and sleep-wake policies. The different nodes can sleep and wake. They have to kind of coordinate in some sense. Whosoever is transmitting to another node, both should be awake, and so on, so as to maximize the throughput in a fair way. Okay, fair is, suppose we are not able to meet everyone's requirement, then meet everyone's requirement to a certain, in a certain way, a fair way. So we consider 3 policies. This is multi-commodity flow model. That's the usual model that people use in the setup. An improvement over that is Steiner tree, that makes use of the fact that these are wireless channels and you can do broadcast. And in the multicast environment, broadcast can help. And of course, afterwards we used network coding, which has been a very active area of research and known to provide better results in the multicasting environments. So this is an example in which we worked. There were 20 sensor nodes, 3 sinks, 10 sensor nodes were multicasting to sync 1 and 2, and 10 sensor nodes were multicasting to 2 and 3. So there is 1, 2 and 3. So all 20 are transmitting, 10 are transmitting to 1 and 2, and 10 are transmitting to 2 and 3. So in this case, we formulated the problem, but it becomes very complex computationally. It becomes a LP, but becomes very complex. So we have a modified algorithm which is somewhat lower complexity. Of course, it's suboptimal, but its performance was found to be close. And for this scenario, this was the this suboptimal algorithm when it was applied to the multi-flow formulation and when it was applied to the network coding formulation. So this is network coding result, and this was the result for multi-flow case. And the curve here is the fraction of data that the network is able to support. So different nodes have different requirements, and you are not able to meet everyone's requirement. So the fair allocation is that you will satisfy certain fraction, and that will maximize that fraction of data that everyone will be able to transmit. And so this provides the network coding based optimization provided more than the multi-commodity case. So conclusions. So we just talked about communication infrastructure has heavy cost of energy consumption and high carbon footprint, so that is of concern to us. But if you do a careful design, you can reduce the energy and carbon footprint substantially. Green communications requires redesign at each level that we talk about, and which means that there are research opportunities for a very large class of people. Everyone in this department has, whatever they are doing, can do research in green communication. And then we have studied and developed algorithms and shown that we can use energy harvesting and have the algorithms in such a way that the random and unreliable energy sources that these are, their effect can be made minimal, because this was one of the concerns and continues to be concern of the designers. But what these algorithms tell you is that these can be as reliable as the usual power grid kind of system. Okay, so this effect of random unreliable, this can be completely taken care of. Thank you. I don't know if I have time for questions.
I think we have time for a couple of questions. So.
Yes, here is one. Oh. Okay.
So I'm curious if there's a general result if you take a channel with a stochastic energy source that you can.
Yes, yes. In fact, that tends to be our guiding principle behind developing these algorithms, and even sometimes the proof techniques can be like that. But still, we found that so we can start with that. We can get an idea what kind of things we expect. But we found that the proving was a little. We had to use somewhat different techniques, and the reason was, see, this is energy harvesting. So in those feeding channels, you can assume that the channel is stationary, ergodic, and so on, and go with that. But here, when you switch on the system, you start with an empty energy buffer, possibly. And then it evolves, the EK process evolves. So it's a non-stationarity involved in this. And to handle that, we had to use somewhat different framework. It's also available, but not a common framework in information theory, what is called AMS, asymptotic mean stationary, that framework, which is there, but not very common. So at many times in proofs we had to keep going back there and see whether the things work or not. So that was it.
So in channels unreliable, we have